Our speaker, Mark Breen. Most of you probably know
Do
him.
you want to do the gloves first?
Oh, I should do that. Thank you. Because if I don't do that, I'm going to be chastised by someone. Not Mark. Anybody recognize these? They were left at the last meeting of last year. And they aren't used. I mean, somebody was better to have a chance.
No one takes them, they belong to the hospital.
Then he put claim on them. Okay, today we have Mark Breen to talk about the nature of weather patterns. Mark's a senior meteorologist, and I have to struggle with that, planetarium director at the Fairbanks Museum and Planetarium in St. Johnsbury. For over 40 years, he has been heard on Vermont Public's Eye on the Sky each weekday morning, and in the afternoons at Vermont Public with the astronomy program Eye on the Night Sky. Who listens to that? Yeah, but you got a crowd here. So along with weather forecasting, his work at the museum involves teaching weather and science, as well as creating and delivering presentations in Vermont's only public planetarium. Originally from Dannemora, New York, Mark has lived in Vermont since attending Lyndon State College, where he graduated, and I won't tell him this one. 1962. 8. Mark made his home. Did I say 62?
You said 61.
That was 82. With a BS in meteorology, he makes his home in St. Johnsbury with his wife Sandy, where they enjoy gardening and golfing in the summer, hunting in the fall, and resting in the winter. That's what it says. Please join me in welcoming Mark Breen.
Thank you, John. Yeah, class of 62, wow. Well, and I have been at the museum. I actually, it's been 44 years, I believe. So yeah, I started when I was very young. Let's see, I'm just plugging this in just because I know how these things happen, where I'll be going halfway through the presentation, my computer will stop working, so we don't want that to happen. Okay, so anyway, yes, so thanks, John. John and I were talking when the last time was that I came over here, because I did come to this building, but we're not really sure. Several years ago, anyway. And so always a pleasure to be here. One of the things that, people sort of wonder, so we have this weather patterns, but Mark Breen, the Fairbanks Museum, what is the museum doing weather forecasting? So we'll find out about that. And I also just want to kind of, I was driving over and I was thinking about weather patterns, and then I was just thinking about patterns. One of the things that humans, you're wired to see patterns. You will see patterns even when there aren't any patterns. Believe me, it's kind of, I think the brain is kind of fascinating that way. But I'm mentioning that because in some ways we'll be seeing some visual patterns. They will, I hope, with the images that I have, that some of that will make sense. That'll be helpful. But also there are patterns that, and I've got a few little clues of it, but an example of that might be red at night, sailor's delight. It is a pattern. Anytime you see a red sunset, the next day invariably is a nice day. So I started thinking about patterns like that. People are comfortable with patterns. And in a lot of ways, patterns are really helpful. I'm thinking of farmers or sailors. If the weather has a pattern to it, a rhythm to it, then you can count on, as though you could count on the weather, but but you can count on, you can kind of plan on, when I see this, the next thing is going to be, right? There's a pattern, there's a rhythm to it. And so those are kind of some of the thoughts that I had, because I have about an hour and 45-minute drive over, so I had plenty of time to think about this. So I just want to kind of throw out these ideas, these little kernels, just to kind of sprinkle them out there to think about as we get started here. Okay, so thinking about patterns. So one of the things, so we have these, I guess I'd call them short-term patterns. And these are ones that all of us are going to identify with. I have several examples of that. But we also need to think about, why do they happen? So then we have to get into, and so there will be kind of this scholarly part of the program. No, there are no quizzes. Don't worry about that. But there'll be some stuff and all kinds of fancy things looking up there. But it all has to do with, how does the atmosphere work? Because that's part of how all of this happens. The other thing that I want to kind of get into is, of course, there are shorter patterns, there are longer patterns, and some of these extended patterns you perhaps will be familiar with, so we'll talk about those. And then finally, there are really long-term patterns. So they're, in some ways, they're not really so much patterns as they are these really long-term cycles of things that go on. So I kind of throw all of that out. So I had mentioned, why the museum doing weather forecasting? Because I can tell you, I don't know of any other museum that does weather forecasting. Okay, and it's not that they can't, it's just, why specifically is this happening? So this goes back to basically the founding of the museum, which is 1891. Museum was built, and if you've never been there, and I'm obviously encouraging you to do that, but it is a marvelous building, still basically in its original state. We just recently completed and opened a brand new science annex. It's the first addition to the building since 1894. We took our time, okay? The planning committees, you wouldn't believe. So anyway, no, but really, it's just an amazing building, lots of natural history. That was kind of the beginnings of it. But then there's a whole ethnological collection, so places around the world. Franklin Fairbanks, our founder, he was, this is the industrial age, so we're going back to the 1800s, and there are a few wealthy families in the U.S. As it turns out, the Fairbanks family at its peak was one of the wealthy families across the nation, and they had the opportunity to travel, but they knew that their workers didn't. And so Franklin was actually committed, and a lot of people say it was his wife, and I have no evidence to doubt that, but to give people in town, if they couldn't travel out across the world, bring the world to them. And so there are all kinds of fascinating things in the museum. But it all has to do with scales. The Fairbanks Scale Company, Fairbanks is actually invented the platform scale back in the 1850s. It became an amazing invention. But Franklin Fairbanks, in his time, he was the nephew of the inventor, he was absolutely fascinated with weather, among all kinds of other things in nature. And so he kept his own weather records. In fact, we're going to take advantage of that. We're going to see some of those. And so his fascination with weather eventually translated to the museum keeping track of what the weather was doing. All right, in fact, we're still doing that. This is in the backyard of the museum where our instruments have been located since 1894. They haven't really moved. They've moved about 20 feet. We had to move them because they were making a parking lot. So anyway, so actually let's talk a little bit about Franklin. So he started his own personal weather records back in the 1850s. About that same time, other people were doing sort of the same thing. And the Smithsonian Institute said, well, wait a minute. Somebody should be organizing and collecting this information. And so he started sending his information into the Smithsonian, which eventually became the U.S. Weather Bureau, which eventually became the National Weather Service. So that's kind of the beginnings of that. Now, somewhere close to 1894, We're not sure if he knew he was in ill health, but it was very close to the end of his life. But essentially, he handed over this process of keeping track of observing the weather to the museum. So here's an example. In fact, it's a little small. I can't quite see. But I picked this particular one. And over on the right-hand side, kind of in the middle, it says Lincoln elected president. Now, the reason I picked that out obviously didn't have anything to do with the weather. One of the things that he did, and one of the things that we still do, is we have a section in our records called remarks. We write all kinds of things. Usually it's some sort of descriptive thing about the weather, because quite honestly, you can put down a bunch of numbers, but it's not the same as saying, it's a glorious day outside. Now, if you read that, that automatically triggers. You just know, I kind of know what kind of day that is, and then you can look at the numbers, and that's fine. So we continue that tradition today. I don't think I've put any elections in there, but that's okay. All right, so in the meantime, those records, as it turns out, are the second longest continuous record in North America. The International Meteorological Association actually recognized this a few years ago. We're one of the very few places that have over 125 years of records. The longest one, by the way, is at Blue Hill Observatory in Massachusetts, just kind of outside of Boston. So the official records that we have are done at 4 o'clock in the afternoon, which seems like kind of an odd time, except in 1894, that was a common time. So in order to keep them consistent, we didn't change it. That's one of the things that often happens with weather records. They change their observing time. They change their observing location. Burlington has a longer observing record. It goes back to 1871. However, they've moved the station 6 times. Anywhere from the shore of Lake Champlain, it was on the rooftop of one of the UVM buildings for several years. It's now out at the airport. These are completely different locations. Our backyard at the museum is our backyard, so everything's pretty standard there. Okay, since then we've added more detailed information. So we have these going back to 1894, but in the 1960s we started adding observations at 7 a.m. and noon. So that was kind of cool. And let's see, this is one of those. Boy, the light up here is terrible. Okay, maybe I'll look at this. Whoa, go back, come back here. Okay. The daily weather patterns. Okay, so these daily observations that we do. All of this is kind of keyed into a sort of a standard. This is a weather map. I'm not going to explain all the fussy little wiggly lines and so forth, but the idea of this larger picture. This is North America, and we've got all of these storms and weather fronts and so on and so forth. And so what ends up happening as these weather systems and so forth go around, move around, is you do end up with, now here's a pattern, okay? And so weekly cold spells. This a couple of years ago just happened to line up kind of nicely. So this is January into February. So on the 4th of January, there was a cold spell. You can see the temperature drops down. But then around the 12th, it's not nearly as dramatic, but you can see the temperature actually drops again. And a week later, on the 18th, the temperature drops again. And a week later, on the 26th, it drops again. I was actually made aware of this particular kind of pattern when I was in high school. I had a great science teacher, and he would post on the bulletin board the record of the temperatures, much like this. He actually had a recording thermometer, actually a pen. The pen went up and down as the temperature changed. And he would post this every week. And he would also put it next to what happened last year. And so you could see the patterns, and all of a sudden the weather pattern, you get this weekly cycle, and all of a sudden something shifted, and it turned into a different pattern for a few to several weeks. But it was kind of my introduction to this idea of cyclical or rhythm kind of weather. Same thing here. Here's a precipitation cycle. I circled it because, again, the writing's kind of tiny. But in February, on the 10th and on the 17th and on the 24th, a week apart, a weather system comes through. That's a really typical thing. If you were to write down, like just on your home calendar or whatever, you would start to notice, oh, and probably you do notice this. I think summer people tend to notice this more. It rains every weekend, right? Or maybe it doesn't rain every weekend. Maybe it rains every Wednesday when you have something that you're planning to do every Wednesday, and it just seems, every Wednesday it rains. It actually is part of this rhythm that the weather gets into, okay? All right, so what exactly is weather? That's really, what's behind all of this is essentially. So here comes kind of the fussier stuff. So, all kinds of stuff to read. You don't have to read that. The bottom line is the sun sends energy to the earth. That is the energy that runs the entire weather system. That's our energy source. And without any surprise here, it's hotter at the equators, colder at the poles. Now the reason that I mention that isn't because I didn't think you knew that. It's just that if it's cold near the poles and it's hot near the equator, hot air rises. So cold air at the poles sinks. It creates a cycle. And that cycle is how basically that energy is moved around through our atmosphere. Now, of course, things get a little complicated. Look at all those squiggly lines. In this particular case, it just simply has to do with the fact that the Earth has a certain size to it. And, it's not necessarily a straight line. Get the warm air to go from the equator up to the North Pole. Things aren't. I wish they were that simple. They're not. Okay. So, but here's this idea that you have all of these things that are going on, but we can actually identify them. So, and I'm hoping this will make sense. So, getting into a little fussy. So we're looking sideways. You can see Africa on the bottom, South America is up on the top, and those red lines are pointing up because that's essentially the equator. If that's where the sun is the hottest, that's where the hot air is going to be. And hot air rises, just like a hot air balloon. So the air goes up at the equator, and what goes up must go down. So about 30 degrees of latitude. And this will be interesting in terms of where this ends up in a second. But for right now, that ends up at about 30 degrees that it sinks back down again. So you have rising air, sinking air. Okay. Then, let's go to where we are because that I think is of interest to us. We have a second location where the air goes up and down. See, in this case though, you see the lines are blue that are going up? That's because it's not the hot air that's going up. It's the air that's colliding. The air that's coming from the pole and the air that's coming from the equator, they meet. They can't go down. They got to go up. And that creates our weather. So our weather is different than tropical weather. No surprise there, but this is specifically, hopefully, a diagram that illustrates that. Okay, now, if all of this were happening on a nice, smooth, ocean-covered globe, everything would be, again, my job would be so easy. But no, we've got all these chunks of land here and there and everywhere. Now, again, without trying to get all fussy about this, but not only are there pieces of land, and that's going to affect how the air is going to move, we also have a globe that's tilted. That's why we have summer and winter. And that changes how much energy different parts of the globe get, and that affects how the weather behaves, how it interacts with our atmosphere. All right, so here's a curious thing. Monsoons. Now, I say the word monsoon, I probably should have just put the word monsoon and not put anything else up. When you think monsoon, what do you think? Rain. That's not what a monsoon is. I know. It's like, wait a minute. Okay, so what a monsoon is a steady seasonal wind. Now, that can create rain, and it does classically in the Himalayas in India, but it's, that's kind of the monsoon that we often think about. But it really is actually generated by the weather pattern created by the land and the heating. In fact, so this is a picture, it says July down on the bottom. July, India, what would you expect? It's hot. Air is rising. Well, in order to take, if the air is rising, something has to take its place. So the air from Asia, from Central Asia, pulls down into there. It's that steady motion that creates the monsoons that we talk about. Also, air comes in from the Indian Ocean, and that supplies the moisture to it. So you've got this kind of collision, so to say, right over the Himalayas. All right, there is actually a monsoon in the winter. But in this case, cold air over Siberia forces the air to basically go from land out to the ocean. No rain. There's no water source because the air is going away from the land and over the ocean. So again, it is a monsoon, and we actually have a monsoon in the US. I didn't put a diagram of it up there, but the monsoon, and I've heard them use this every once in a while, on some television sort of description of the weather. There is a monsoon in the southwestern US. For the same reasons. The heat in the southwest causes the air to go up. It gets moisture that comes in from the Pacific. I have a few friends that live out in Phoenix year-round, and she's actually a former meteorologist. And she knows, you get into June and July, and all of a sudden they get these incredible gully washer kind of thunderstorms in the middle of the desert. But and it happens regularly. It's a pattern. It's actually a monsoon. Okay. All right, so from there, again, I need a big screen. Okay. But essentially what we've got here is we have, and this is how again, it's a pattern, right? Near the South Pole, in the winter, there's this huge area of high pressure. High pressure means sunshine, today's high pressure. But for the South Pole, and this kind of fits into the South Pole's weather, and a very less known fact, let's say that. The world's largest desert is Antarctica. The average snowfall at the South Pole, any guess? How much snow do you think they get at the South Pole every year?
0 inches.
Not 0.
2 inches.
Close. 5. but that's exactly the kind of category. Here we easily get, 60, 70, 80 inches of snow in the winter. A snowy winter will get over 100 inches. Way more snow than they get at the South Pole. On the other hand, the hottest temperature at the South Pole ever, well, I shouldn't say ever, since 1952, 10 degrees. So it doesn't melt, obviously. So anyway, but these actually, so the land creates that particular pattern. There is no land at the North Pole. I was just watching, Will Smith actually did this great series from pole to pole, and he went up to the Arctic and he actually dove into the Arctic Ocean because there is no land up there. So high pressure in the northern hemisphere doesn't form very well over the ocean. It actually likes to sit over Siberia. Actually, we saw that with the monsoon. It also forms over northern Canada. In fact, there's a chunk of it right now on the south shore of Hudson Bay. It's 35 below zero there this morning. So, not coming here, by the way. Okay. All right, so having mentioned a little bit about this, and we saw this diagram before, but I want to kind of work this into what goes on. So we have cold air that comes from the pole, that's off to the right. We have warm air that comes up from the tropics, off on the left. They collide, they push the air up, but something else is going on. We're spinning, the Earth spins on its axis, and what that does is it creates this curious zone right where the two warm and cold air meet, and this zone is called the jet stream. Now, so the jet stream, and I've seen this, and this is not wrong, but I'm just thinking of other visual things that you may have seen. Television, they talk about the weather pattern, and what they're always showing is the jet stream. So the jet stream, actually I had a great story about the jet stream because, and this is, since I have been doing this for a couple of decades, or 5, met one of the pilots from World War II that flew between Japan and Alaska. They were flying reconnaissance missions. And so his job was to fly from our base in Alaska to fly over Japan and then come back with, information. So they fly down, and then on his, and it's taking him, like 8, 10, 12 hours to get there, but he comes back, it's only like 3 hours. His commander is absolutely livid. What were you guys doing? Were you flying around on someplace else? He says, you won't believe it. Way up, 30,000 feet, we were flying into winds that were 150, 200 miles an hour. And the guy's looking at him like, no. But yeah, that's really the discovery of the jet stream. All of a sudden you put aircraft up there, jet stream, and suddenly they found there were these rivers, these currents of air up above us. Well, they really are the byproduct of where the cold air from the north and the warm air from the south, where they meet, and of course where they meet decides where it's going to be warm or cold, and it creates these strong patterns. Well, that wind, of course, if it's going 200 miles an hour, is going to move weather systems, hence the pattern. And okay, so here's kind of a quick diagram here. So in this particular case, the 75 meters per second, that's the 75 that's sitting in the middle of that screen there, 167 miles an hour. Okay. Now, it's not all that fast. Some it goes faster, sometimes it goes slower. We're actually going to see that that affects things. And again, it's where the warm and cold air meet. Well, that's going to change with the seasons. So the jet stream, the orange pattern up there, that's where the jet stream is in the summer. In the winter, cold air expands, so the jet stream shifts southward. So does the storm track. In fact, we often get into a period of time where the storms seem to all go to our south. And that's why the cold air expands. Okay? All right, and so again, here's a kind of a visual look at the fact that this jet stream, it doesn't go, it's not a smooth little undulation. It can get pretty wacky. Huge. Well, if you think about this particular image, you've got up near northern Canada, as I'm looking right in the middle of the screen, there's air that goes from northern Canada almost all the way down to Florida, which is what it did this year, by the way, all right? But that's why it was so cold in Florida. Or conversely, the air is going from near Southern California all the way up into northern Canada. Obviously, they get a lot of warm air by that kind of pattern. So we have what we call high amplitude, low amplitude patterns. All right, so it doesn't stay the same. I mean, if it stayed the same, again, my job would be easy. I probably wouldn't have a job. But so we have changes that go on. And so in this, I think the nice thing about this diagram, there's all these verbiage in there. The blue indicates cold, red indicates warm. Now, the air is going to circulate around that, and it's going to change. That's the beauty of weather patterns and changing. It's also the challenge is to figure out when that happens. So, in this diagram, one of the things that actually does show up, if you look between the L and the H on the left, there's this red arrow that goes up into the H. It's basically, it's increasing the warm air in a place that's already warm. It's going to enhance, it's going to make that pattern even more amplified, a bigger, stronger area. So, well, actually, you can see it actually does it here. So it went from a relatively even L, H, and L, low, higher pressure, lower pressure. Now it's enhancing. Now, that doesn't stay the same either. It can't just continue to increase and decrease. So, what usually happens is you start out, everything's kind of balanced out. The cold air's in one place, the warm air's in another, and then something happens, some kink, some little bend, and things start getting enhanced. In fact, they get so enhanced that little pools, little kind of collections of cold get separated. This is going to, I hope, I think this will illustrates something you probably heard a lot about it, and I say the last 6-7 years, because there are chunks of cold air that come from the Arctic and then they come down and they sit over the United States or other places across the globe, but we call it the polar vortex. So, all right, so I don't know who in the media grabbed onto this polar vortex idea, that suddenly something happened and the weather completely changed, and a polar vortex, oh my gosh, it happens every year. Yeah, every cold spell that you've seen, welcome to the polar vortex. In fact, you probably hear a lot less about it because, all right, we heard about that. Come up with a different name. Actually, going back to when I was young, and maybe when some of you were young, the Montreal Express. Oh yeah, well, that's still the polar vortex. It's just a different name for it, right? Okay, so anyway, these chunks of air do indeed move around. And so, I just mentioned a cold spell. Isn't that a pattern? Isn't that, you know, oh, we're in a cold pattern. All this cold air is sitting here. So, now, kind of going back a little bit, again, when the jet stream is kind of level, it's not really going up and down too much, we get what we call a zonal flow. This is kind of an ordinary, run-of-the-mill, you know, weather systems go through about every 2 or 3 days. It stays cold to the north, stays warm to the south, everybody's happy. Now, well, I don't say that everybody's happy, but especially the people in the middle. One of the things that happens, though, is that, and you saw this before, just a little hint of it, these areas of warm air sometimes get enhanced, they build up, and they can actually get separated from that blue line that runs across the top there. That's where most of the air is going. So separated from that, there's this bubble, this dome of hot air, and it sits there. And you get some sunshine, you get July and August, and you end up with a heat wave, okay? So this is all, and the other thing that happens, okay, got this big circulation, you know, the air is coming around and around, and all around the outside edge of it, it's colliding with stuff. And that means if it's colliding, the air's colliding, we're getting clouds building up, we're getting storms, and and sometimes we'll hear this expression, but they call it a ring of fire. This big dome of hot air, there's no cold air around, so it just sits there. But where there is contrast between the hot and the cold, clouds build up, you get storms, and so you will get storms all the way around the outside edge of that. That's the ring of fire, so to say. Those are thunderstorms that would happen. And in fact, one of the things that happened here, this is going back a few years now, but in that same flow, in fact, I'm just going to go back just a second. So we have a northwest airflow. Now normally, northwest, it's out in the middle of Canada, it's a dry airflow. But if it is hot air that's pushing against the cold air to create that northwest airflow, we can occasionally get some of our worst thunderstorms. This happened, I think it was the first year. No, 2 years. I was at the museum for 2 years, 1984, Amtrak in Williston. There were like 6 inches of rain all in one night. Tremendous damage. Well, this was a similar situation, but this happened kind of a run from Barrie over to St. Johnsbury, where 6-7 inches of rain fell through the night. Huge but localized flooding. Okay? All right, so another pattern that develops, and again, I tried to come up with examples of things that you've heard of. So the Bermuda High. Now I have it as the Bermuda Azores High, just because thinking a little bit more globally here, but we often talk about in the summer the Bermuda High. It sits out near Bermuda, what a surprise, but the air around it, that red arrow, steers warm tropical air around it. It comes up the east coast. Those are our heat waves. Now, that high, and I guess I should say the water sitting out east of the United States gets warmer through the summer. In fact, it doesn't reach its peak temperature until September. Anybody that's gone swimming off the Maine coast in May or June knows this. It takes a while for the water to heat up. And so I mention that because late in the summer, with that warm water, we get hurricanes. And those hurricanes actually take advantage of that particular pattern. So it's a reason that hurricanes will sometimes curve up through the eastern U.S., and they kind of come in spells. So this was a period of time, and in some ways this is a pattern, but more of a cycle. But in the 1950s and early 60s, there was a string of hurricanes that came up along the East Coast. And naturally, you get a hurricane every other year, you're probably not going to build a nice fancy cottage right on the edge of the shore. What happened? Came the 1970s. There weren't any hurricanes. 1980s, there were no hurricanes that came up. Well, there was one. So people started building. They built all kinds of things along the coast. Wasn't that lovely? Until the hurricanes started coming back. It's a cycle. Okay, all right. In fact, speaking of hurricanes coming back, Hurricane Irene. That has been part of, and we've seen a few of these events lately because this is a longer term cycle. We'll actually talk a little bit more about the part of that cycle. But the idea is that there are some 30 to 40 year sort of cycles. Again, this is a pattern, but these cycles of lots of hurricanes, very few hurricanes, lots of hurricanes, very few hurricanes. Okay, obviously, Irene, a tremendous event in Vermont, kind of the second worst disaster that we've had, although kind of a close call with the other flooding that we had just 2 summers ago. Okay, so I talked about this area of high pressure and nice sunny weather and high heat wave. So this is the other separation that goes on, what they call a cutoff low, but very often I like the phrase, the wheel of misfortune. If you're underneath it, day after day after day, it's rain, it's clouds, and and it happens, if it's going to happen, spring. Okay, so this is a cutoff low. It's an area of low pressure, but it's also an area of cold air. So it's basically a leftover clump of winter air that came from the pole, dropped down, it's sitting there. There's nothing, because it's now separated. There's nothing to move it out of the way. That's why it sits there. That's why it's the wheel of misfortune that just sits there. So another pattern that can sometimes develop is you can get, okay, the fancy name is a Rex block, but so you get warm high pressure, H, up above, this is on the west coast on the left-hand side, and then cold low pressure down below it. It's a balance. It's actually quite happy to stay just that way. Okay, but it creates a pattern, and it creates cold air consistently coming from, you can see where that blue line starts up in northern Canada, it comes right down into the middle of the US. Well, if you put that airflow right over the Great Lakes, oh boy, Buffalo, blizzard of 1977. I actually lived in Potsdam, but not at that time. And so, I mean, there was one weekend, I remember getting 4-foot snowstorms, 8 feet, yeah. But these tremendous, patterns, the air is going to sit going over the Great Lakes day after day after day. Some places had over 100 inches of snow from that particular blizzard. That was just the snow that fell. That doesn't say anything about the winds blowing it to 20, 30-foot drifts out there. Another part of that same pattern that you just saw, and this happened in 1978, the blizzard of 78 in southern New England. So they just had a blizzard, right? And there were lots of talk about, oh, that's just like the blizzard of 1978. Nope. It was the worst blizzard in Providence, Rhode Island, and a couple of places next to Providence. But the blizzard of 1978 covered all of southern Vermont, southern New Hampshire, all of southern New England. It was a much bigger storm, much bigger event. So one other, and these are, they sometimes call these blocking patterns because they just kind of sit there. It's shaped like the letter omega, and that's what they call it. Kind of a logical thing there. But again, it's balanced. And because it's balanced, things don't change, and because you're stuck in it, you get the same weather day after day after day. Now, you may be stuck in the sunshine. You may be stuck underneath one of those wheels of misfortune. Okay. Okay, so now we're going to expand this idea a little bit. We are an ocean planet. Okay? 75% of the Earth's surface covered with ocean. That's going to have an influence. Now, one of the things that I think about with this is that the ocean temperatures are pretty much the reason for all of these weather patterns that we've talked about. It's why they set up to begin with. Okay, so we have, and this is, in this way, this is just simply the water temperature. Okay, it's warm near the equator, cold near the poles. Well, there's no surprise there. What is, I think, more helpful, in fact, it's what meteorologists use, is we don't care what the temperature is. Well, we do, but more importantly, it's the comparison to the average. So this is called an anomaly. Let's not get too fussy about it, except where it's orange or red, it's warmer than average. Where it's blue, it's colder than average. And so this starts to illustrate for us, where is the air going to be warmer than average or colder than average? Now, some of this changes, but it's all part of, and this is something that scientists are studying, but this one, we haven't unraveled all of this mystery yet. And that's because there is what they call a global circulation with the oceans. In fact, this global circulation, in some cases, may take over 1,500 years. That's longer than I'm going to be working. Okay, just saying. So, but this is, so what that's saying is there could be an event going on, let's say in the Pacific right now. It may not affect the Atlantic for hundreds of years. How to keep track of that? Well, we don't even have observations, obviously, going back several hundred years, although they have been able to, with ocean sediments, they've been able to kind of get an idea about how these patterns have been working over hundreds and hundreds of years. So I say all of this, all this kind of background, because this is what you often hear about. You can see the top, there's a lot of blue near the equator, so just to orient you, that's the Pacific Ocean over on the center and left. Blue near the equator on the top, red near the equator on the bottom. The top is called a La Nina. The bottom is called El Nino. So El Nino, that name, that phrase, has been around since the 1500s. Mostly thanks to a Peruvian fisherman. Off the coast of Peru, pretty much every Christmas, the water turned the water turned warm and the fish all left. Cold water has a lot of food for fish. Warm water doesn't. So there was a pattern, and pretty much every year, somewhere near Christmas, they basically, well, let's take a break anyway. And so El Nino means the Christ child. That's where the name comes from. Okay, so it wasn't really until the 1960s that they had a little bit better observations. 1960s, so more than 300 years after all of this, they start to get some idea about it. And then, 1982, a tremendous El Nino takes place. Very warm water all across the Pacific equatorial region. It completely changed the weather patterns in the US, and suddenly people are like, wait a minute, what's going on here? And so recognizing what the ocean was doing became a huge effort starting in the early 1980s. And so we now it's something that we pay close attention to. We also, it has to do with basically, and you can see the difference without getting into any fussy details. If you look on the top, you see thunderstorms kind of on the left and then toward the center, and then on the bottom, kind of the opposite. And that's El Nino, La Nina, they are the opposite. Warm water, cold water, it changes where that energy basically is placed. Now, it also changes, so what happens in the Pacific then happens, further down, everything's going from in this case, left to right or west to east. And so in an El Nino pattern, up above on the top, it's very warm up across the Pacific, northwest, and then lots of storms down in the southern United States. With a La Nina, it's really cold out in the Pacific Northwest. Well, at least it usually is. This is one of those, there is never a single answer, because the bottom is actually what the weather pattern was doing this year. Sort of. I say sort of because here's the other fussy details. Oh, now you got warm water that's in the middle. It's not on one side or the other. And you got some cool water where it's normally warm. There's actually, it's called El Nino Modici. Like I said, they keep studying it. They have to come up with new terms because they find out more information about it. But here's, okay, so forget the names and so forth. What does it mean? What does it mean for us? Well, here's the El Nino Modici. This was January to March 2014. And I specifically point that out because it was a cold winter. It was a preview of the coming winter. And so what happened during that winter? The red is the jet stream, and you can see it started in northern Canada, came down and around, brought us lots of cold air. But here's the next year. February 2015. It was, it turns out, if you combine that with January and March of 2015, it was the coldest January to March in over 100 years. So, El Nino, La Nina, doesn't really matter in terms of the names. It does matter in terms of where the water is warm, where it's cold. There's another interesting, globe is warming. Pretty much we're all familiar with that idea. But a warming globe doesn't necessarily behave the way you might think. For example, on the left-hand side is El Nino, and the orange indicates, in case El Nino, warmer water, warmer globe, indicates fewer tornadoes. A warmer globe may lead to fewer tornadoes. The right-hand side is La Nina, cold water. Cold water, and the purples that are on there indicate greater numbers of tornadoes. So, just kind of mention that, it's one of those things don't always kind of fall in place the way that, logic would seem to dictate. Okay, so again, more about El Ninos, neutrals, so on and so forth. We've been talking about the Pacific. There is this other ocean, the Atlantic. It does the same sort of thing, but it doesn't have this equatorial thing and the fancy names and so forth, but it does have patterns. It does have cycles, I really would like to say. So, and here's part of that. Starting around 1960 and through about 1990, a cold period in the Atlantic. Why do I mention that? When everybody says, oh, the old-fashioned winters, like it was in the 1960s. Well, okay, no question. Lots of snow in the 1960s and early 70s. But there's all that cold. If you go back, even into the 1950s, I can remember having this conversation with somebody at the museum. Oh, I grew up in the 1950s. It never rained in the winter in the 1950s. I said, really? Let's look, since we have 130 years of weather records. And sure enough, it rained in the winters. In the it snowed too. I'm not saying it didn't snow, but there's I don't remember it raining. I said, why would you remember it raining? There's nothing exciting about it raining. It's like, ugh, you know. So anyway, so I mentioned that because there are these cycles that we see in the Atlantic, and they have actually have been able to build that back into the 1850s. So there's a kind of some somewhat warmer water in the 1850s through the 1890s, and then it gets colder in the early part of the 1900s. It gets warmer in the middle part of the century. It gets colder again in the 60s and 70s. It's warm now. I think logic dictates where it's going next, okay? But I'm never saying that the weather is logical, okay? The other thing is, okay, so you've got the Atlantic and what it's doing. Now you have the Pacific and what it's doing. What if you combine the two? So now what they are looking at, so you'll notice they're not quite, they don't always match up. Like in the 1960s and 70s, they're both cold. In the right around 1950, they're both warm. And those actually mark specific periods of time that are warm or cold. Right now, both of them are on the warm side. You got reds on both, on the right-hand side. So it's been warmer. Again, no surprise there. We have one other, I'll call it a wild card of sorts, because this is an area of ongoing study in particular because this just happened a few years ago. Now, it's not that we didn't know that there were undersea volcanoes, but we didn't have the kinds of satellite measurements that we now have to really start to see the effects of an underwater volcano. So this underwater volcano went off east of Australia called Tongo. This is 2022. Okay, so that's 3.5 years ago. Huge eruption. Now, here's what I found very fascinating, is they looked at the ocean temperatures east of Australia. See all that red? That's where the volcano erupted. Now, up to this point, I have not heard a whole lot of discussion about how much energy is coming out of the ocean vents that are sitting under there, undersea vents, undersea volcanoes, and how is that affecting the water temperatures in various places. We haven't studied it a lot, so we don't have an answer to that yet. But it is kind of a new area in terms of trying to study it. They have noticed, for example, there may be a connection to those warm periods in the Atlantic with increased volcanic activity. Don't know that? Again, that's why we're studying it. In fact, this is the latest picture. In fact, I grabbed it yesterday just so we could see, these are the ocean temperatures in terms of comparing it to normal. And again, not a surprise. Again, a warming globe, we do have warmer water temperatures, but that blue that's sitting in the middle of the Pacific, that is our weather maker for this year. Oddly, the warm, you can see the kind of patches of red in the middle of the picture there, that's moving off the coastline of Japan and heading toward the west coast of the US. Depending on the timing, that could set up an interesting winter next year. Let's just call it interesting. I am certainly not going to predict next year's winter today. No way. But I just mentioned that because where these blobs really of warm and cold water go is going to dictate as how those weather patterns either develop or how they change over periods of time as well. All right. Whew. So that is a kind of a broad overview of these various cycles, but going from things that I hopefully, I think a lot of us can relate to that, like I said, it rains every, Tuesday or whatever, those kinds of things, all the way out to these bigger patterns that, again, we notice these changes. We know that it was cold in the 60s and 70s and we had lots of snow. And then actually a niece and a nephew. Now, they were born right around 1980. They remember, in the 1980s, and they were born in January. they remember a lot of birthdays that they couldn't have their sledding party because there was no snow. Okay, so different time period, different pattern. My kids, let's see, my kids, so that's late 90s and early 2000s. They're growing up around the year 2011, 2012. Couple of, I mean, I have a picture of my daughter standing on the pile of snow that came off the roof so that her feet are up about the height of the roof. Okay, it was the year, I think that was 2008. We just had, so again, you know, the weather, it kind of comes and goes. Lake Champlain froze over this year. Now there is something, again, we can see changes to that. It used to freeze over about every other winter. Now, it wasn't a cycle of every other winter, but about 5 of 10 winters it would freeze over. The last decade, it's only frozen over 3 times. So, is that a change, or is that part of a cycle? I guess I will know in about 20 or 30 years, okay? So, okay. All right, so that's really what I had to share with you, but do you have any questions that you'd like, you know, we can kind of poke around with this? Yes?
Can you bring up your last graphic?
I probably can. Let's see. This one?
Yeah.
Okay.
Yes. So this year, there was a lot of reporting about the atmospheric river that hit the west coast and the coast. So is that little blob of blue that's above the big blob of blue?
Actually, so there is a little kind of smudge in the middle of the Pacific. Those are the Hawaiian Islands. And it's actually in that warm channel between the 2 blue pieces, the one near the equator and the one a little bit farther to the upper left of that. And so that's where some of the energy came to create that atmospheric river that they talked about. Yeah?
Has that been a pattern that's recurred?
Yes, so atmospheric rivers, again, much like you know, the polar vortex, it's been around for a long, long time. Every once in a while, you know, media kind of enhances its awareness. So, okay. Yeah. I thought so. Yes?
I just have a question. How do you determine the normal highs and lows?
Normal highs and lows, great question. So, because the weather records at the museum are 130 years long, you could think, well, we'll just use that average. But we don't. Because the weather changes, and because a lot of reporting stations, observation stations, they don't have as long a record, so they, a long time ago, settled on 30 years as a climate period. And so we advance that every 10 years. So the current climate period is from 1990 to 2020. That 30-year period determines what's the average or normal temperature.
What average are you using?
No, that's what we would use right now.
No, but you're telling me it's like a 30-year period. Are you using mean or, you know, you've got all these numbers.
Oh, okay. So if we're talking about the average temperature, we're talking about the mean temperature. You take the daily high, daily low averages together, and then you add that up through the entire year. Now, of course, we can do it annually. We can do it, you know, by season. We can do it by month. Okay. So we use all of those. Yes.
Well, before the question, one thing that makes me crazy is listening to weather forecasters on TV using normal when they mean average.
Ah, okay.
It's,
Three averages.
the question I have is, if you had to press into a corner, what would you say the basic difference is between a cycle and a pattern?
Oh, what is the difference between a cycle and a pattern? In some ways, there isn't a distinction, but the distinction that I tend to make, and kind of how I view what I presented today, is that cycles are things that I see that happen over certainly multiple years or really decades. And so the Pacific warms up and cools down over a period of 30 to 40 years. Same thing in the Atlantic. And so that, to me, is more of a cycle than a pattern. Whereas something shorter term, whether it's where the jet stream is, and of course that would dictate what the weather is until the jet stream moves. And so you change the weather pattern. Okay, so I guess that would be the distinction that I probably make.
If if I could sneak in one more quick question.
Yeah.
Why is it that, this may be more of a question for a biologist, but why is it that the warm areas of the ocean have less nutrients than the cold areas when it seems counterintuitive? If you have a still, warm, stagnant puddle, it grows a lot more stuff than a cold one.
Well, I know that one of the primary food sources, part of the food chain in the ocean, are plankton. And plankton do much better in cold water. In fact, that you will have to ask a biologist. Yep, kind of drifted out of my field of expertise there. So, but yeah, I mean, it's why actually the oceans, the Arctic and Antarctic oceans are teeming with life, but it's the nutrients that are involved. So it may have to do with maybe there's less oxygen in the water. I shouldn't even guess. Check with the biologist. Yes.
So these days when a storm is coming, we'll hear in the forecast that there's the European model and there's the US model. And why are we hearing more about that? And is one model a little more spot on than the other?
It varies. So it varies from season to season, year to year. So a computer model uses, well, those observations that I talked about at the museum, there are literally thousands of places that report, and that data is collected now, kind of almost an instantaneous basis. So that data goes into the computer. The computer then has a series of mathematical calculations that it does. And so it's a numerical computer model. And so it basically does the calculations, it comes up with an answer. And they use different equations on the European model because they developed it in Europe than the US model. And so those are the ones that you hear about. There are actually hundreds of models. And sometimes there are like 30 models that all get kind of smooshed into one blend of a model. So there's all kinds of things. There's a Canadian model, there's a Japanese model. And I look at them because, well, for example, right now, and they're always constantly monkeying around with these equations. But right now, the European computer model doesn't see cold air. We don't know why. I'm sure they would like to know why, but they're fussing around with it. But so, in other words, 3 weeks from now, if it's showing that it's going to be warm here, suddenly, in that 3-week period, it'll go, oh, no, wait a minute, it's going to be cold. It's one of the reasons that long-range forecasts are not reliable, because we don't understand the atmosphere very perfectly. And so, so I mentioned that the computer models vary. Some years, for reasons that I certainly can't explain, a computer model, it finds, it's got the right situation or whatever, and it gets the storms right every time, and the other computer model is out to lunch. And then all of a sudden, and sometimes certainly without warning, I'm relying on this computer. Oh yes, it's going to rain on Friday, and suddenly, oh no, it's Saturday. Oh, now it's a day off. Okay, so you start looking at the other one and go, oh, wait a minute, this one actually was a better, projection. So different models, scientists are, constantly, and computer models are just that. They're models. So I still rely on the window. It's turned out to be a really valuable weather instrument.
I have a question about weather and its forecasting and artificial intelligence. So is there much discussion going on in your world about AI?
Let's say that.
AI, is there much discussion going on?
Oh, there's discussion. In some ways, AI is such a broad, amorphous sort of term. I mean, they're obviously, it's basically how a computer is designed, where it takes the information and what it put out when it has an error, it's supposed to learn from that error and improve it. Right now, a lot of the AI models that I'm seeing, they're kind of lurchy. I'm not really sure that's a word. In other words, oh no, there's this big storm, oh tremendous storm, blizzard. And then the next model run, oh no, high pressure, nice and. So it doesn't have the consistency, it seems, built in. And that probably will come with time. Until we have more, time to look at them and they have more time to develop, we'll have to wait and see how they eventually turn out. So.
One final question for Mark, please.
I'll probably mess up the terminology. Global climate change.
Yes.
Used to be called global warming. All of your careful graphs show hot versus cold, but do you have data that shows deviation from either the average or the median with mean? And as a scientist, is global climate change something that you see, or is it a scare tactic?
Yeah, oh, okay. Well, that's a loaded question, isn't it? So, a couple of things about that. So, one, long record at the museum. I can easily see that the temperature at the museum has warmed approximately 2.5 degrees Fahrenheit from the beginning of the record to now. Most of that warming actually took place through 1950. Then it cooled off in the 60s and 70s and is now gone up and now past. So in other words, it warmed up, then it cooled off. Now it's a little bit warmer than this kind of dip that was down in here, okay? And globally, one of the challenges with the global picture and one of the values of a record like the museum's record, we warmed up, but we didn't warm up because somebody built an airport next to us or around us. That has happened to some of these observing sites. And Burlington is not to be excluded from that. Burlington is now sitting at an airport with tarmac, and Burlington's airport is getting bigger. I can't believe that that's not having some influence on their temperature profile. So there are certain records that are more valuable because they're a little more consistent. So there's different networks of observations. They're trying to discern as best as possible what is due to the situation versus what's happening, with human influence to the atmosphere. So I'm definitely seeing some effects from it. Again, our museum record isn't influenced by other things. One of the other things that I found really interesting about our museum record is that we also found it's also getting more humid out. Now, that ties into a couple of things. First of all, the Arctic is warming more than the equator. It's also getting more moist in the Arctic. And moist air doesn't cool off as much at night. It also doesn't warm up as much during the day. At the Fairbanks Museum, the hottest temperature we ever had was 101 degrees in 1944.
Wow.
That's the last time. So more humidity, daytime temperatures are actually slightly lower. Nights, especially in the winter, are warmer. So there's all kinds of fussy things that go on with it. So I can't really give you a single, snapshot answer. But I can say that yes, we're noticing the warming taking place, and so it isn't a scare tactic. I think. And this is in some ways, I guess this is me, but it's certainly the museum, because it's in our mission statement. People should be better stewards of the earth. We should take better care of the earth. It's the only one we've got, right? I know that's kind of cliche in terms of saying, but on the other hand, why would you go out of your way to make it worse, right? When, it could be simple things, recycling, all those kinds of things. And I know, sometimes it's poo-pooed, but if everybody kind of tended to and took better care of the planet, maybe we wouldn't have this discussion. So, okay, great.
Mark Breen.
All right, thank you, guys.